So that's a joint work with James Van Brecht and Xavier Bresson, who is just here. Okay, so let me start with a very cartoonish picture, and I apologize for this. I'm just trying to make a point. So, I mean, we think of deep learning algorithm as algorithms that learn features from the data. That's kind of, that's kind of the hallmark, at least what we think of deep learning algorithm. We have very little theory about them. I mean, we mostly have an empirical understanding of, they are very complex systems, and we mostly have an empirical understanding of what type of guarantee and how this works. And yes, they generalize very well in practice. Compared to what we think more as classical machine learning, where we would often use predetermined feature, let's say like SIFT feature. Often the algorithm turn out to be convex. We have very good understanding of them. The solutions are very well defined. We have theoretical guarantee about generalization. So the point is, learning feature, we think of it as something very good, and we think, sorry, I'm struggling with the pointer a bit. And I think I'm just, yeah. So we think of learning feature as, being a key part of obtaining good generalization. We also know that we pay a big price for algorithms that learn feature from the data that make everything very complex, non-convex, and we don't have much theoretical understanding of this complex system. So that would be, a very important question would be, can we make this type of understanding more formal? Can we try to capture something analytically about why learning feature from data give very good generalization? That's obviously a very hard question. What I am going to try to do is to drill down on a very specific discrete data model, try to run the counting and combinatorics to understand the situation in this very simple data model, and see if we get anything about this intuition that learning feature from data lead to very good generalization on this specific simple data model. It's like speaking about deep learning and generalization, trying to prove stuff about this, I think is very hard. Let me mention two difficulties in particular for trying to understand this, in my opinion. So the first one is quite obvious, and I'm just going to quote here a paper from Aurora, Cohen, and Luo. The deep learning seems to kick in only with certain type of data, so not with random data, for example. And we lack mathematical tool for reasoning about real life data. Okay, I'm not going to paraphrasing. I think it's said perfectly. Hard to get result because it seems to work only with data with specific structure, and it's hard to do this. Okay. Another difficulty, which I'm going to spend more time speaking, it is I think that often when, as practitioner, we do deep learning, I think we are often in this realm that we have the training set, the data set have many categories and subcategories. But many of these subcategories are very, very poorly sampled, maybe 10 to 100 examples per subcategory. And that's making very hard to get that means if we are in this realm, like getting asymptotic performance guarantees based on large sample limit is not very useful. Like getting statement like the test error is order of 1 over, let's say, the square root of the number of sample per category. It's not going to be very illuminating if I have only a very few sample per category. Let me spend a bit more time speaking about this. So a long tail distribution is something looking like this, where you have the head of the distribution that is here, and the tail of the distribution contains a significant portion of the mass. It is quite well known that natural data typically follow this type of long tail distribution. So this is an example from this paper where they counted the number of example per object class in the Sun data set. So window and person, you have lots of them. Okay. Rope, spoon, and locker, well, they're semi-rare example, and these are the very rare example. But this is a long tail distribution. Basically, it doesn't decay exponentially. It's more like it's decay like a polynomial. If I make a cartoon view of this, so you would have the very common example window and person, which are in the head of the distribution. The ones which are quite rare are in the tail of the distribution, but if your algorithm can only do the common thing, you're not going to do well because you're going to get at least 40% of the error because the rare example collectively form a significant portion of what you're doing. And it's very hard to avoid if you deal with real data that it's never going to be enough to do only the very frequent things. You really need to focus on the tail of the data because it's a significant portion of what you are doing. Okay. This long tail behavior, you have it at multiple levels. You also have it at the level of subcategories within categories. So if you look at the category of bus, so that's still from the same paper capturing long tail distribution of object subcategory. If you look at the bus category, yes, the head of the distribution, you will have many bus which are basically facing frontward like this. The tail of the distribution, you will have a bus from backward or cluttered bus or things like this. And again, the tail of the distribution here is a significant portion of your data. If you can only recognize a bus facing frontward, your algorithm is going to fail. Same thing here, within the category person facing frontward is the most common in the data set. But you will have person on a horse or person doing this on a computer. And you need to be able to deal with this case because it's long tail. This is a significant portion of your data. So I'm updating this picture where basically you have the head of the data, which are the very common stuff, window, standing person, bus view from the side. And then you have the rare object, rope, person on a horse, bus viewed from the back, which are here. And this is the most important to some extent. I mean, that's, if you can only recognize this, your algorithm is not going to be good. So you really need to focus on the rare subcategory to some extent. Yes, so we have many subcategories that contain only a few examples. And that's why doing asymptotic performance guarantee based on large sample limit might not give you something very useful when you're working in this realm. Okay, so that was the two difficulties that I wanted to mention. So what we will try to attempt on our very specific discrete data model is so we will study generalization on a very simple data model, but for which it's exactly a data model on which we would expect deep learning to kick in. So that's intuitively we'll take a data model for which we expect to be a deep learning algorithm to kick in. Okay? And on this simple data model, we will try to do some non-asymptotic analysis. So we have what we want to do is not to focus on the order, but really on the constant in our test error. Okay. And we will do this by doing some combinatorics in the detail for this. Oh, sorry, I'm repeating myself, but let me make just this as a last point in this direction of doing non-asymptotic analysis. To some extent, what I want to argue it is that this might not be the regime of interest. So here I'm comparing two regimes where the number of subcategories is small, maybe 20 subcategories, and within each subcategory, I have a large number of samples, maybe 3,000 samples per subcategory. I think this more like, let's say, a MNIST data set where you have, a small number, a number of category or subcategories that you think as fixed, and a number of sample per category that you think as being large. Compared to a regime that I think more, let's say, a bit more like ImageNet, where you have a large number of categories and subcategories. So maybe you have 10,000 subcategories. You have 1,000 categories, and within each category, you have like 10 or 100 of subcategories. But many of these subcategories have only, 10, 100 samples in them. So I want to think more of a regime where the number of samples per subcategory is kind of constant, but it's the number of subcategories that is larger. And I would think that it's actually an interesting regime, more mimicking what we have in practice because stuff are long tail. And okay. So let me now describe the simple discrete data model on which I'd like to drill down and see if we can learn something valuable about this. Okay. So we are going to consider, hopefully as simple as possible, of a latent model. So here I have a vocabulary in this example of 12 words. Okay. So potato, carrot, leek, lettuce, cheese, butter, yogurt. These are my 12 words. And this vocabulary is partitioned into 3 concepts. These are the veggies, the dairies, and the meat. Then I have latent variables, so that I will call sequence of concept. So for example, here I have a sequence of concept, dairy, veggie, meat, veggie. The latent variable generate your observed variable, which are sequence of words. So for example, this sequence of words was generated by this sequence of concept. So I have concept dairy, I randomly choose a word in the dairy concept and get cheese. Then I randomly choose a word in the dairy concept, get butter. I randomly choose a word in the veggie concept, which here get lettuce, etc. Okay. So these are my latent variable, and generate my observable variable. So I have sequence of concept generating sequence of words according to this partition of the vocabulary into concept. So this would be the observed variable or training set. In this example, I have 3 categories. Okay, and if you look at in the first category, I have 2 subcategories. I have one which contain only a few samples, so here only 2 samples. And I have a common subcategory that contain 4 samples. So you see in category 1, there was 2 latent variables, one that generate a subcategory with only 2 samples, and another one that generates a subcategory with 4 samples. So that's the full latent model. Basically, it is designed so I have a certain number of categories. Within each category, I have a rare and a common subcategory. So I have a category with few samples. So here it's 2 samples. This is what I will call N rare. I have only 2 samples in the rare subcategory. And I have a subcategory with many samples. Just to fit the picture, many here is 4. And this is the other subcategory. So that's why if I have 3 categories, I have 6 latent variables, 2 latent variables per category that generate the common, that generate the subcategory with a high number of samples and the subcategory with a low number of samples. So now at test time, if I have a test, so I will call them sentence, the sequence of words, I will just call them a sentence. So if I have a sentence which is generated by this sequence of concept, that's going to be hard. That's going to be hard because my training set contains only two samples. So this sentence was generating from the subcategory, which has a small number of samples, only 2 samples. And this is hard to classify because, well, I mean, I picked this example in purpose. Here you see that there's no intersection between the word of my test sentence here and the 2 trained sentences from the same subcategory. So butter, here that cheese yogurt, butter. You see, I have no intersection because I have too few samples in this subcategory. So the long tail nature of the data set make it hard because I have subcategory with very little samples. And if I get a test example from this subcategory, it's just hard to deal with. But we don't expect a neural net to have trouble with this kind of thing. At least a neural net with the correct architecture should do this very easily. What we think as practitioner of what would happen. So let me describe like a simple neural net that exactly match this architecture. So I have a sentence here, a sequence of words. Each word will receive an embedding or a word representation with maybe a MLP and here a layer norm. Detail doesn't really matter. So here each word will receive an embedding, and this is shared everywhere for each word. What we hope is that the neural net will learn that butter and yogurt are in the same concept and should receive exactly the same embedding. That's what we would hope. We would hope that potato and lettuce, the neural net will learn it is in the same concept and that they should receive the same embedding. The problem was designed that the only thing that matters to determine the category is to know what is the concept associated with each word. So we would hope that the neural net will learn that the only information that matters is the concept, and then it will learn to give the same embedding to each word that belongs to the same concept. Okay. Okay, so let me summarize the data model. So the idea, so these are the observed variables. I'm trying to do as simple as possible of a latent data model in which I have some long tail behavior. I have some subcategory with many samples and subcategories with very little sample. Intuitively, we would expect this data structure to be easy for a neural net with the correct architecture. We would expect a neural net to have no difficulty to solve this. On the other hand, we can see also that something that doesn't learn feature, an algorithm that doesn't learn feature, we would expect it to struggle because of this. I mean, if I have a test sentence from a subcategory which is undersampled, it seems that it would be hard for something that doesn't learn feature to solve this problem. Okay, so to try to clarify the motivation here is that we will see that, I mean, if you run a code on this, it's crystal clear, like a neural net will solve this perfectly. Something that, like a SVM or something like this, will completely fail on this. I mean, when you run experiments, that's quite crystal clear that there's no what's happening. I am trying to have a data model which is as simple as possible and for which there is some hope to have like some clear bound on, you know, if I don't learn feature, I am going to fail. If I learn feature, I'm going to succeed easily. Let's say, for example, if you try to understand what's the difference between a linear model and a non-linear model, the XOR problem is the first thing you go to. That's quite obvious. You look at it and say, oh yes, I need a non-linear model. Here I would like something as simple as possible, where if I have an algorithm that learns feature versus an algorithm that doesn't learn feature, the one that learns feature should succeed, the one that doesn't learn feature should fail. and I'm trying to get a data model as simple as possible to see if I can prove something here. And that's what we are going to try to do here, to try to prove that, to prove, yeah.
Trying to understand your terminology. So feature is a concept. Are they equivalent?
Yes, basically that's, yes, a feature, I mean, okay. So, in this context, that's exactly what it will turn to do. Like basically, learning the feature means to be able to learn the underlying partition. That's exactly, so, okay, let me put it slightly different. An obvious problem when we discuss, okay, what is good about learning feature versus not learning feature is, well, what do we even mean by learning feature? I mean, what does it mean to say that a SVM doesn't learn feature? Well, I mean, does learn something. So what, I mean, interest of a problem like this, it's indeed, it's give a very clear context to what we mean by learning feature. Without the structure in the data, it doesn't really make sense to speak about feature. And here I'm trying a structure as simple as possible so that it's crystal clear what learning feature would mean in this case. But I will formalize more after what I mean by learning feature. Okay, so what we will do is mostly a negative result in these things to show that algorithms that do not learn feature fail to generalize on this data model, and we will derive a theoretical upper bound for the success rate of algorithms that do not learn feature on this data model. There's some caveat to this statement that I will make clear later. For this, we currently only have empirical results. So empirically, it's easy to, I mean, we can run experiment and see that the neural net that I showed before completely succeed on this data model. I have good hope also that we can prove that, I mean, that's what we are working on now, to have a proof of these empirical things that we have right now. I think there's good hope that we can prove that a simple neural net can solve this problem. But I will mostly speak of this result today, that algorithm that doesn't learn feature, we can quantify exactly the penalty for not learning feature on this data model. Okay. The easiest way to explain the theoretical result is start by showing the experiment and then to explain what we can prove from this. So these are the results of experiments where we try various algorithms. Okay, so the neural network that I showed you, then nearest neighbor algorithm on the top here, psi star and psi 1 hot are feature map that map sentences to RD. So psi 1 hot is the obvious feature map. Take your sentence, do a 1 hot encoding of each word of your sentence, concatenate them. Psi star, I'm going to discuss it later. This is basically the best possible feature map in this problem. So on the top of this feature map, like the 1 hot embedding and the optimal feature map, we run either a nearest neighbor algorithm or a SVM algorithm. And here what we see is the success rate. I have to explain what each column means, but we see success rate here, okay? All these success rates are terrible. They are below 1%. The opposite is the neural network is getting close to 100% accuracy on this. So these are run on a specific instance for the parameter which are here. This is a specific instance. So here, in this example here, I had 12 words in the vocabulary. Here, I have 150 words, okay? We had 3 concepts. I have 5 concepts in this example. The length of the sentence are 9, and the number of categories is 1,000. So I'm thinking a large number of categories, okay? Now, how many examples per category? So again, in my mind, what I'm interested in is the case where I have a large number of category and subcategory and a constant number of sample per category or subcategory. So in this example, if you remember, basically I had a undersample subcategory that had 2 samples and a category which has 4 samples. These are the n rare. This is the number of samples in the rare subcategory, and n common is the number of samples in the common subcategory. So here I'm looking at always case where the common subcategory has always 5 samples, okay? And the rare subcategory has a number of samples that go from 1 to 5. And note that in this last column, there's no more distinction between common category. I mean, we are really in the realm, which is actually the ones I care, where it's constant number of samples per category. Let me maybe show you this picture. So here it was 2 and 4. What I'm considering in the table, it is always 5 for the common one, and the undersample one go from 1 to 5. How do we run the experiment? So, well, we have this 150 word. We randomly generate a partition of this 150 words into the 5 subcategory. Then we randomly generate the sequence of concept, okay? And that gives us basically the task. When this is fixed, these are the latent variables which are fixed. Then we generate from the latent variable a train set and a test set, and then we evaluate our various algorithm. Neural net, the 2 nearest neighbor, and the 2 SVM. Okay. The evaluation is only done on the rare sentences, but that does. I mean, that's what are these numbers, but that wouldn't make a big difference too. Again, here in the last column, there's no more difference between the undersample subcategory and the one which has more sample. Okay, so now we can look at the numbers. So yes, it's clear that the algorithms that learn features success completely, empirically. The ones that do not learn feature fail completely. Our theoretical contribution is this, and the big caveats I mentioned earlier, it is that we are just going to work with nearest neighbor for this thing. So we are going to consider the best possible feature. Okay, yes. So what we're going to prove it is the best possible feature that you get for this problem. If you use a nearest neighbor classification rule on this best possible feature, you are going to your success rate is going to be lower. Than this, and so the formula here is and this is a formula which is specific to this. I mean, we have a general formula for general case, but in this case, this will be what you will get. So 0.015, the number of sample in the undersample category, plus 1/1000. And this is an evaluation of this formula when you plug the number of rare sample into this. And so you see that indeed here you get an upper bound for the success rate, a theoretical upper bound for the success rate, which is, I mean, not super tight, but also not vacuous at all. I mean, it's tell you this upper bound on the success rate show you that yes, I mean, it's really not. It's really not. I mean, you're really not doing some. It's not doing good. Okay, so let me explain a bit more. So here, so psi 1 hot, this one, as I explained, that's the trivial feature map where you have a sequence of words. Each word get a 1 hot encoding. You concatenate all this. So that's the trivial feature map for your sentences. A feature map that I will call psi perfect is like the perfect one, the one you'd like, which you have the sequence of words. Each word receives an embedding corresponding to its concept. Okay, so butter receives the embedding for the concept dairy. Carrot receives the embedding for the concept veggie. So that would be the perfect feature map where you have completely solved the problem. because if you have this perfect feature map, everything will work. So the accuracy will be 100%. If you consider a hard test point, which is this one, with a perfect feature map, the word butter will have the embedding for dairy, which will be the same embedding that for this and this. So the embedding of my test sentence will be exactly the same that the embedding of these two trained sentences in the correct subcategory. So you completely solve the system, the problem, like your test sentence, at the exact same embedding that the trained sentence in the correct subcategory. But obviously, this is cheating. Sorry. I mean, this map, in order to build it, I need to have knowledge of the partition. There is no way I can, in order to have this feature map that associate to each word the embedding of its concept, I need to know the partition of the word into concepts. And so a natural question is the following. So is there a feature map from the data space, here it is a space of sentence, to any Hilbert space, which is better than the trivial map? So the trivial map, psi1 hop, doesn't assume any knowledge of the latent variable, and that we can construct without a priori knowledge of the partition of the vocabulary of the latent variable, basically. Okay. And the answer is yes. So there is a feature map which is better than the trivial feature map and doesn't assume any knowledge of the partition of the vocabulary into concept. That's what we are going to call psi star. We can prove it is the best possible feature map if you use the nearest neighbor classification rule. Okay. We have an explicit formula for this optimal feature map. We can then leverage, so we can then use this and try to estimate what is the success rate of this best possible feature map. And so that's by doing this, so that after become mostly combinatorics, by estimating the success rate of this optimal feature map, we can bound the success rate by some formula which with the specific variable will give you something like this. Let me be more formal. So that would be exactly the theorem that we are proving. It is pick any feature map, meaning any map from the space of sentence to any possible Hilbert space. Then randomly generate a partition, randomly generate the sequence of concept, randomly generate a train set and a test set, run a nearest neighbor algorithm on the feature extracted with this map. Then the expected success rate is smaller than this. And expected is with respect to all the random stuff that happen here. And this is true whatever is the feature map, including the best possible feature map. So if you fix a feature map first, then do this, you are guaranteed to have a success which is smaller than this. So it is very much like the no free lunch theorem in classical learning theory. If you first fix the feature map and then you are given the task, then you can prove that you are going to fail on this data model. On the contrary, empirically, right now, the neural network completely succeeds in this case under the same circumstance.
So what's the loss function for the neural network?
Here it was just so when we train it, that was just a cross entropy. And then after we can do, once the neural net learns the feature, you can also just do a nearest neighbor, you will get the same success rate. And all the numbers here are accuracy. Yeah. And so why does this capture the idea of learning versus not learning feature? if we think of what typically we mean by an algorithm that doesn't learn feature, we often mean that we are going to use a set of features, let's say like SIFT, that have been proven useful on many applications, and basically we are going to use them off the shelf without tailoring them to the specific task. So here that corresponds to choosing your feature, like the best possible feature for this problem, before to know what's going to be the task. Before to assign the to partition the vocabulary into concept, and before to generate the sequence of concept. Again, the interest it is here. There's no difficulty for the neural net to do this. Where here you can probably show that the best possible feature map is going to fail if you use the nearest neighbor classification rule. Empirically, we see that replacing the nearest neighbor classification rule with the SVM, for example, is barely giving you any improvement. So you see that you are still failing. We don't have proof for this. The proof is only if you use a nearest neighbor classification rule. Okay. Okay. Yeah.
I don't understand what's the difference between not being able to learn the feature and not having a model, a classifier of high dimensionality. Like you could just throw the data into higher dimensionality to a nonlinear regression. Does that count as learning the feature? Sorry, regression. I mean like a regression classifier.
So you mean like if I'm in high dimensional enough, it's always going to be separable if I put. But this just tells you something about the training set. So it's turned out that this data, getting a training loss equal to 0 is not difficult in this case. The question is how it's going to generalize on previously unseen sentence. I don't know if I understood your question.
You didn't try it, right? I feel like the comparison against neural network was that you either you only look at the data space without doing any feature transformation versus doing the feature transformation you're going to show.
Yes.
The alternative would just be throw the data into higher dimension.
So here, this is allowing the feature map can throw in this theorem. The feature map can throw your data in as high dimension as you want. Even in infinite dimension, you will still get this error even if you throw them in infinite dimension. Here I am allowing for a feature map to take sentence and to throw it into possibly an infinite dimensional space. That's not going to help in terms of generalization. Like the problem that you can, so you can always get like the training loss equal to 0, but the problem you are not going to be able to solve if you don't know this, it is how do you know that a test sentence like this one is supposed to be like these two other things because in your train set, you have only 2 exemplars that are similar to this, and that might not be enough to be able to determine what is the correct class of your test sentence. We can discuss this. I see that I'm not answering your question to your satisfaction. Let's see. We can discuss this after. Okay. So what I was saying it is that this order of first choosing the feature without knowing what are the latent variables, then generating the task, the train set and the test set, and is what intuitively what we would think of not learning learning feature. Okay. So this I keep writing this, which is a specific case for the I don't remember what's like 150 words and So there is a general formula behind, which there's a good reason I didn't show it. It's a mess of, so there's the first part. So this is the upper bound on the accuracy. This is something, I'm going to discuss it briefly in a minute. This is something which is very much like an entropy. This is the kernel associated with the best possible feature map. And this gives you something which is, so here you have the number of samples in the undersample category. And then, well, this is quite clean, okay? And then you have to estimate this quantity, and this become really counting and combinatorics, and you get stuff which are not nice. The point is we work like very, very hard to get this as tight as possible so that it's, to get something meaningful. So what we wanted it is, to have something that shows that the success rate is smaller than 3% or smaller than 6%. And this required like going quite deep into trying to estimating this stuff like as close as, as tight as possible estimate. Okay. I just want to spend a minute explaining what is the best possible feature map in this problem. So, again, we are looking for the best possible feature map, assuming no knowledge of the partition of the vocabulary into concept. You see that this best possible feature map do slightly better, barely, than the trivial feature map. So the trivial feature map is just one hot encoding. If you take the best possible feature map, empirically, you see you're barely above it. Okay. But obviously, what matters here is to have a proof that what is the best possible feature map so that we can get an upper bound on the error. So the best possible feature map is quite intuitive. So it's easier to be understood through its kernel. So by the kernel of the best, so the feature map take a sentence A or a sentence B and map it to some Hilbert space, okay? This quantity is easy to understand. So take the dot product of the feature extracted on this sentence and the feature extracted on this sentence up to constant, and we don't care about it. And what is it? It will give you, so the dot product of this is the number of partitions of the vocabulary that make both sentences conceptually equivalent. And I have to explain what I mean by conceptually equivalent. It is quite simple. So K star, I will call K star the kernel associated with the best possible feature map, okay? And so that's going to give me the number of partitions of the vocabulary that make basically both these sentences the same, okay? Quick example, so let's say that I have two sentences like this, okay, word 1, word 3, so I still have 12 words, but I stop giving them name because it's confusing if I give them name, okay? Here I have 3 partitions of the vocabulary, okay? These 2 partitions make these 2 sentences the same, conceptually equivalent. This one doesn't. What do I mean by this? If I look at the first 2 words in the first 2 sentences, both of them, whether I look at this partition or this partition, belong to the same concept. If I look at these 2 words, same thing. If I look at these 2 words, so, well, obviously word 6 and word 6 will always belong to the same concept, whatever is the partition. If you look at this, word 2 and word 5 belong to the same partition, to the same concept here and to the same concept here. Meaning that these 2 partitions, when you look at these 2 sentences, if you just focus on the concept, these 2 sentences are exactly the same. Okay, so that's what I mean by a partition make 2 sentences conceptually equivalent. Basically, if you replace the word by the corresponding concept, you get exactly the same thing. This one does not, because you see word 1 and word 8 belong to 2 different concepts with respect to this partition. Okay. So why does it, so our kernel K star So will give us a measure of similarity between sentences. And this measure of similarity is exactly, you don't know the partition of the vocabulary into concept. So the measure of similarity is the number of partition that makes the two sentences the same if you replace word by concept. Okay. So if my two sentences are the same, like this example, any partition will work. Whatever partition I take, that will always work. So this measure of similarity will be very big, like the number of partition is all the possible partition, and okay, that match your intuition. If now I have two sentences, let's say that differ only by one word, which is the first word here, the number of partition of the vocabulary that will make these two sentences the same, it means that word 1 and word 8 must always end up in the same concept for these to work. So I have to look at all the partition with the constraint that all the partitions that put word 1 and word 8 together. So there's still a lot of this partition, but there is less than if I didn't have this constraint. Okay. If I look at two sentences like this, so now I need word 1 and word 8 to end up in the same concept, word 1 and word 5 to end up in the same concept. So all these three words must be in the same concept. I also need word 10 and word 3 to end up in the same concept. So now I am looking for the similarity between these two sentences, all the partition of the vocabulary that put together these three words and these two words. And you start to have much less of them. So the more differences you have between the sentence, the smaller is the measure of similarity given by K star. Okay? And intuitively, that kind of makes sense that would be the best possible measure of similarity for a problem, because if we assume no knowledge of the underlying partition of the word into concept, and I am asked to determine whether two sentences come from the same category, basically what I should do is, well, think of all the possible partition of the vocabulary into concept, see how many works make the two sentences the same, and if there is a lot, it's likely that these two sentences come from the same concept. Bottom line being, if I don't know a priori what is the partition of the vocabulary into concept, the best thing that I can do is try all possible partition and see how many work for what I am doing. Okay? And that's what gives like the optimal kernel for the problem with the associated optimal feature map. And that's where you see all the combinatorics and the formulas that are going to pop in. You end up to have to solve a combinatorial to have to study a combinatorial problem like this. And that's, I'm going to stop here. Yes?
One question here is like you are modeling this kind of first order kind of relationship, but there's no model of the high order relationships, right?
Correct.
So you have these two in the same group, but they may be in a different group for different.
That is completely correct. So the model is arguably very, very, very simple, so that we can run the analysis. It's also to some extent for what I want to do now. That's what I want. I want to try to get the simpler stuff for which I can see the SEPA is clear when learning feature, and there's no claim to be realistic, but there's just a claim that it captures something that would still exist in a more complex model. But yes, that's completely correct. And yeah, I just wanted to point before to stop. It is the ugly stuff here are coming from this. So like the optimal feature map end up being like a kind of graph cut problem. So, each time you have two sentences that force words to be together. So basically each vertex here is a word. When you have two sentences that make a graph on this word, and then you are counting the number of partitions that do not cut the graph. And that's where you start to end up with type of quantity like this, because you're counting some essentially combinatorial objects behind, and that's where this is come. Again, the pain was really to get this as tight as possible. And let me just say one word about this, which was the key quantity here. So this thing comes out very naturally, like you write down the problem and the error, and basically these quantities start to pop in, which is, it's very much like an entropy. If you have if you apply it to probability distribution, if the probability distribution is flat, then you will have a very low value for this. If the probability distribution is concentrating, that will give you a high value for this. And this quantity is quite nice, it's convex, you can prove lots of stuff out of it. And that kind of the clean part of the thing and the soft part of the, so we called it like a permuted moment because it kind of looks like the moment of a probability distribution, and then you maximize over all possible permutation. I don't want to go in detail. The point is very much like an entropy, that the natural quantities that popped in when you study the specific discrete model, and that gives you the soft part of the thing. So you can directly estimate this by the permuted moment of the optimal kernel. The hard part after become how do you estimate the permuted moment of the optimal kernel, which is done here, and that's where all the stuff comes. Okay, and I will stop here. Thank you.
Thank you, Laurent.